Today we will begin section 3.4, day 5, metallic bonding. What is metallic bonding? So in a metal, we have the nucleus of our metal, and the nucleus of the metal has a positive charge. Now, the valence electrons of the metal, let's just give this metal a name, for example, let's just say it's gold. The nucleus of this metal has a positive charge, and then there are valence electrons that gold has. And gold can change, but let's just say it has a valence electron of 2. So what happens is that the 2 electrons that are in the valence shell of the gold atom are actually free to move about from one valence shell to another. So basically, all of the valence electrons from gold are constantly being lost and gained on the outside shells of the gold atoms. So because the gold atoms are losing those electrons and simultaneously gaining them, we say that in metallic bonding, we have these positive cations or positive metal ions because they are temporarily charged because they're losing electrons that are within what they call a sea of delocalized electrons. And what that sea of delocalized electrons is basically those valence electrons from the gold atoms that are jumping from one valence shell to the next. So the electrons are mobile, and we will see how this sea of delocalized electrons accounts for a lot of the properties of metals. So here it shows the metallic bonding of gold, and we have, again, these positive gold nuclei, and then the valence electrons from the gold are all sort of able to freely move about this delocalized sea. Because there is this mobility of the electrons, in figure B, it shows you how and why metals conduct electricity. Because if you send an electric current through a metal, the delocalized sea of electrons basically carries that charge from one side to another. If you take a look at C shows you how the structure of metals allows them to be good conductors of heat. Heat is sent, say, from one side to the other, and because of the delocalized sea of electrons, it carries that energy across the structure. D shows how this delocalized sea and the structure of metals gives them their malleability and ductility. We said that malleability and ductility is the sort of flexibility of the metals, because when you shift, say, a section of the metal nuclei, the nuclei are going to shift over. But the delocalized electrons, because they're sort of sharing this sea of electrons anyway, will sort of stay in place. So it allows a pressure or force to be applied to a metal without ruining or breaking the structure. It allows that flexibility of the structure because these nuclei of the metals are sort of floating around in this flexible sea of electrons. So these points talk about those previous pictures. In A, the outermost electrons wander freely through the metal. The metal consists of cations held together by negatively charged electron glue. So that's referring to picture A. Picture B shows free electrons can move rapidly in response to electric fields, hence metals are good conductors of electricity. So this one shows you why metals are good conductors of electricity. C, the free electrons can transmit kinetic energy rapidly, hence metals are good conductors of heat. So this was that one. And then D, the layers of atoms in metal are hard to pull apart because of the electrons holding them together, hence metals are tough. But individual atoms are not held to any specific atom, hence atoms slip easily past one another. Thus metals are ductile. Metallic bonding is the basis of our industrial civilization. So metallic bonding, the structure is made up of delocalized electrons, where those electrons are free to move about the lattice. It is a strong bond. The ions, positive metal centers or nuclei, are held together by the strong electrostatic attraction of the negative electrons. Bond strength increases as the positive charge on the ions increase. So if you have gold, which has a positive 2 charge, versus, let's say, gallium, which has a positive 3 charge, gallium is going to have a stronger bond strength because it has a greater positive charge. A decrease in the size of the metal ions increases the bond strength. The smaller the size of the metal ion, the closer they are packed together, the stronger the bond is between the positive cation and the negative sea of electrons. And increases in the number of mobile electrons and atoms, bond strength does. Metallic bonding and properties. Metals have high melting and boiling points. It takes a lot of energy to weaken the strong attractive forces between the metal ions and the delocalized electrons. Metals conduct electricity because the current flows because the delocalized electrons are free to move. And metals conduct heat due to the movement of delocalized electrons and vibrations passed on from one metal ion to the next. There are 5 structures that we are going to talk about, and we have talked about them, but this section sort of summarizes the structures that we've seen in this section. The first is simple atomic. That just means the structure of a normal neutral atom. Simple molecular is just the structure of a molecule, 2 nonmetals covalently bonded sharing electrons. Giant ionic just means an ionic compound made between a metal and a nonmetal where the electrons are transferred. Giant metallic is the one we just saw a couple minutes ago in the delocalized sea of electrons being held together to the positive metal cations. And then giant molecular, we'll touch upon 2 examples of giant molecular here at the end. Get this slide. Okay, so there is a table in your notes that looks like this, and you're going to fill this table in as we go through it here. Okay, so giant ionic is first. Example of giant ionic is any ionic compound. The giant part is just something that the ACE people like to put in front of the word ionic, but it's just normal ionic that we've been talking about. So 2 examples, NaCl and MgO. Again, it's between a metal and a nonmetal. The particles present in an ionic compound are ions, the positive cation, the negative anion. What keeps the particles together, the force that keeps them together, is the electrostatic force between the positive and negative ions. The physical state at room temperature is solid. Ionic compounds have high melting and boiling points. They are hard and brittle. They conduct electricity only if they are melted or dissolved in water. As a solid, remember that those ions are so held close together that they cannot allow electrons to move about them. So in the solid state, they do not conduct. And their solubility, most are soluble in water. Ionic compounds have a lattice structure. Many ionic, metallic, and covalent compounds are crystalline. A lattice structure is a regular repeating arrangement of atoms, ions, or molecules in a crystal. The regular structure is due to the regular repeating arrangement of the particles within the crystal. For ionic lattices, they are 3D arrangements of alternating positive and minus ions. The size of the ion determines the type of lattice. There's different types of lattices, but you just have to know that a lattice is a regular repeating pattern of atoms, molecules, or what's the other one? Ions. So here it shows you a lattice between Cl minus and Na positive. This one shows separation between them, and then A shows if they didn't have those lines between them, what it would look like. Giant ionic compounds have high melting and boiling points due to the strong force of attraction. The strong force of attraction requires a lot of energy to break the particles apart, thus high melting and boiling points. Okay, which ionic compound has a higher melting and boiling point? We have sodium chloride on the left, we have magnesium oxide on the right. The correct answer is magnesium oxide. There is a higher charge density, meaning that magnesium is charged +2 and oxygen is charged -2, whereas sodium is charged +1 and chlorine is charged -1. Over here, it's different. So a higher charge density, like you see in magnesium oxide, increases the force between the ions. Giant metallic. So giant metallic, any metal, any single metal by itself, copper, aluminum, titanium, tin, any metal is going to have a metallic structure. Particles present, the positive ions of the metals that are surrounded by that sea of electrons. If this was ever asked in a test, this is the key to describing a giant metallic structure. The positive ions in the sea of electrons. The forces that keep them together, the delocalized sea of electrons attracting the positive ions. Physical state at room temperature, solid. High melting and boiling points. They are hard and malleable, good conductors of electricity, and they are insoluble in water. Again, metal lattices are ions surrounded by a sea of electrons. Here it shows you the metal nuclei, and then it is surrounded by this mobile sea of electrons. Here's another example of where these green atoms represent the metal positively charged nucleus or nuclei, and then these black dots represent the free electrons that are able to move about. The ions are often packed in hexagonal layers or cubic arrangements. The strong attractive forces causes most metals to have a high tensile strength and hardness. The delocalized electrons move all around and reform bonds. So for example, this picture on the left shows you what a normal metal structure looks like. If you apply a stress to it, what happens is that the positive nuclei just shift over, but the delocalized electrons just find a new valence shell to kind of hang on to. So it causes that malleability and that ductility for metals. Metals conduct electricity because that charge can be carried through that delocalized sea of electrons. Simple molecular just means a molecule, and a molecule is just a covalent compound. So it's going to be between two nonmetals where the electrons are shared. We saw a couple days ago. So iodine, which is diatomic, which is I2, which is why it's not an atom. Bromine, which is Br2, and carbon dioxide, which is CO2. The particles present are molecules. And by the way, this is a really good table to study from because it summarizes everything in a nice, organized way. The forces that keep these together are the weak intermolecular forces, the covalent bonds within the molecule. The physical states are solids, liquids, or gases at room temperature. Molecules have lower melting and boiling points. They are soft, they are non-conductors, and they are usually insoluble in water, but soluble if polar to form hydrogen bonds. I know it's hard to see that last thing right there. It says to form H bonds. Simple molecular lattices. Substances with a simple molecular structure can form crystals. This is due to the regular repeating pattern in the lattice structure. Giant molecular is the last type of structure. There are only 3 giant molecular examples that you have to be responsible for. One of them is graphite, one of them is diamond, and then silicon dioxide. So a giant molecular structure is a molecule. It's between covalently bonded things, but they are slightly different than simple molecular because their structure is more advanced and more intricate. The particle present are atoms. The forces keeping them together are strong covalent bonds. They are solid at room temperature, very high melting and boiling points, very hard, non-conductors except for graphite, and they are insoluble in water. So the giant molecular lattices, covalently bonded with 3D network of covalent bonds through the whole structure. This is an example of graphite. Those atoms are carbon atoms. They have high melting and boiling points due to the strong bonds between the carbon atoms, like in this hexagon layer right here. But remember that between this layer and this layer, there are very weak forces holding those layers together, which is why graphite is soft and diamond has a different structure, and diamond's structure is a little different, which makes it harder and not soft like graphite. So again, there are strong forces within the carbon atoms on each layer, but between the layers, there are very weak forces in graphite. For diamond, the carbon atoms are all bonded in a 3D intricate complex network. So there are very strong covalent bonds between those carbon atoms, which causes diamond to have an extremely high melting and boiling point. It also causes diamond to be very hard because of the extremely strong bonds between those carbon atoms. And silica, which is silicon dioxide, which is glass, has a very similar structure to diamond, where for every one silicon there's 2 oxygens, but then all of the SiO2s are all bonded together within this intricate 3D network. Remember that an allotrope is a different crystalline form of the same element. So carbon graphite, and carbon diamond are examples of allotropes. They're made up of the same element carbon, but they are arranged differently, and that arrangement gives them different structures. Elements such as carbon and compounds such as SiO2 can be giant molecular structures. And so this is another picture of the graphite. Remember, I keep saying there are strong covalent bonds between the carbon atoms in each layer, but then there are weak bonds that hold the layers together for graphite. The carbon atoms form planar layers. The layers are arranged in hexagons. Graphite has a high melting and boiling point due to strong covalent bonds. Its softness is due to the weak forces holding the layers together. And remember that graphite has 3 carbons attached to every carbon. So there is a free electron that can move along the layers, which is why graphite conducts electricity. The 4th electron becomes delocalized. Diamond, each carbon has 4 bonds, so it does not conduct electricity because there's no delocalized electron to carry a charge. It is crystalline. It has a high melting and boiling point due to the strong covalent bonds. Hardness, difficult to break the 3D network of strong covalent bonds. Does not conduct electricity because all the electrons are involved in covalent bonds. Silicon dioxide, which is SiO2, has a similar structure to diamond, where those red atoms represent silicon, the blue atoms represent oxygen, and then each SiO2 molecule is 3D bonded or intricately complexly bonded to another SiO2 molecule. So it gives it similar properties as diamond. And that is where we will end day 5.